As you know, today's lecture was supposed to be the second of three, but we got snowed out for the first one. So Michael is going to try to compress the three lectures into the remaining two, the one today and the final one on Wednesday, which will be at 6:15 p.m. in the philosophy department seminar room. And in each case, we will run approximately an extra 15 minutes and not take an official break so he can say everything that he wants to say. We didn't want him to come all the way out here and have to cut back on the wisdom he is going to impart to us. I think Michael Friedman, so let me just say a little bit about the format of today. He will speak for roughly 40 minutes, and then we'll take a 15-minute Q&A. And after that, the second half, followed by as much Q&A as there is time for, which will probably be about half an hour. So it's taxing, but I'm sure it'll be worth it. Michael Friedman is unique, I think, within philosophy and possibly even outside of it, in the range of his interests and the breadth of his knowledge. He has done important work not only in the philosophy of physics, the philosophy of science, on logical positivism, but on a range of German philosophers from Kant to Heidegger, including all the people in between, namely Fichte, Hegel, Schelling, Schlegel, you name it, who are central to the continental tradition and who tend to be ignored by analytic philosophy and indeed often regarded as the lunatic fringe. So he has not only bridged the analytic continental divide, but he has cast light on its nature and its origin. Because time is pressing, I'm going to keep this introduction short. His topic today in these lectures is the origin of the notion of scientific philosophy from Kant to Kuhn and beyond. Please join me in welcoming Michael Friedman.
Well, I want to thank Paul for inviting me and setting this up. I'm very grateful and very happy to be here. First we have a little quiz. We have to identify, because I didn't put the names on here. So let's start with the one that may be easiest. It's either in the middle or here. So, who is the next easiest? I don't know. What about the one in the corner up on the left? Schelling, good. Helmholtz. Poincaré. Okay. So all of it was Einstein and all these people weren't supposed to be here for the first lecture. Just Schelling, Kant, and some Hegel. But you will be spared Hegel because of lack of time. So the original plan was to have these three lectures, Scientific Philosophy from the Kant to Kuhn and beyond. And basically today I'm putting together 1 and 2, although I've compressed things and left a lot out, hopefully to make it work. And the third one is really the beyond part, where I'm going to try to present my own newest ideas about how to be a neo-Kantian philosopher of science today. And that will be the last. Oh, somebody took it. That helps, Paul. So one thing I want to say, though, is that I'm not going to have time to do much in detail about Kuhn. People may be disappointed. You might want Kant and Kuhn to be at least co-equal. That's what it looks like in the poster. So what I have done is I've actually published a number of things about Kuhn in the last 10 years or so, and 2 of those papers have been forwarded electronically to the department here. And there's a sign-up sheet out there. If you put your name and your email address, you can be hooked up so that you can get copies, electronic copies of those 2 things. And you'll kind of know what I've already published about Kuhn and also Cassirer. And I will say a little bit about Cassirer and Kuhn in the last lecture, how they both need changes and they need more intuition and less concepts. And I'll say the same thing about myself if there's time. Okay. Kant's notion of pure natural science is familiar from his Prolegomena to Any Future Metaphysics, 1783. Can you hear me okay? Yes? And the second B edition of the Critique of Pure Reason in 1787. Both of which aim to correct some of the misunderstandings which, by Kant's lights, had surrounded the appearance of the first A edition of the Critique in 1781. In particular, Kant now, in the Prolegomena and the second edition, organizes his investigation around the question of how synthetic a priori cognition is possible. And he further divides that question into the three sub-questions of how pure mathematics is possible, how pure natural science is possible, and how metaphysics as a science could be possible. Kant takes it to be an actual given fact that the first two, math, natural science, are already possible as instances of genuine synthetic a priori cognition, and he aims to explain on this basis how metaphysics too could or can attain that status. And as indubitable examples of the already given instances of pure science, math, natural science, Kant presents some simple mathematical examples from arithmetic and geometry, including 7 plus 5 equals 12. And in the case of pure natural science, he presents versions, instances almost, of Newton's laws of motion. And this is the part about the conservation of the quantity of matter, inertia, and the equality of action and reaction. And by the way, in the first handout, you should have two handouts. One is for the no longer given first lecture, and that's number 1 on the handout, but you can see it here also. Kant only, I want to distinguish pure natural science in Kant's view from proper natural science. Kant only articulates his conception of proper natural science in the preface to the Metaphysical Foundations of Natural Science, which appeared in 1786, closely preceding the second B edition of the Critique in 1787. The revisions Kant made in the second edition of the Critique were rather extensive, including a complete rewriting of the transcendental deduction of the categories, as well as significant changes and additions to the transcendental aesthetic on space and time, and analytic on the principles of pure understanding, such as that of the permanence of substance and the principle of causality. And most dramatically, in the refutation of idealism that appears only in the second edition. All of these changes taken together underscore the fact that what Kant means by phenomena or appearances are not purely psychological states inside our heads, but rather physical bodies in space and time interacting with one another in accordance with necessary laws of motion. Of course, space and time are transcendently ideal. We can worry about that later. Kant organizes the 4 main chapters of the Metaphysical Foundations, like so much of his philosophy, in accordance with his fourfold division of the table of categories in the first Critique, the famous architectonic. So we have the 4 sets of quantity, quality, relation, and modality. Quantity means unity, plurality, and totality. Quality, reality, negation, limitation. Relation, substance, causality, community. And modality, well, you know, possibility, actuality, and necessity. The first, quantity, generate a priori constraints on our experience deriving from the purely formal properties of space and time as pure forms of intuition. The second, quality, generates such constraints on the empirical content or matter, any empirical content or matter, that may fill these forms, involving both extensive and intensive magnitude of the space and time filling matter. The third, relation, generate constraints, law-like necessary connections, on the relations between such filled regions in space and time. And the fourth, the categories of modality, generate no additional a priori content of their own, but rather keep track of the epistemic status of the successively stronger and more extensive constraints generated in moving from stage to stage in the application of the categories of quantity, quality, and relation, respectively. The 4 chapters of the Metaphysical Foundations follow a similar pattern. The first chapter on pheronomy, that is motion, considers matter as a mere moving point, lacking both mass and force, for example, and shows only how the velocities exhibited by this moving point can be added to and subtracted from one another. The second chapter on dynamics first considers the filling of space by matter, which, according to Kant, takes place by means of the two fundamental forces of repulsion and attraction, which together balance out somehow to give a determinate degree of filling. The third chapter on mechanics then introduces the Newtonian concept of mass, or quantity of matter, and formulates a variant of the Newtonian laws of motion. I already mentioned that. Kant formulates more specifically what he calls the three laws of mechanics: the conservation of the total quantity of matter, the law of inertia, and the equality of action and reaction. These laws are supposed to be realizations for Kant relative to the empirical concept of matter, movable, impenetrable, and mechanically interacting corporeal substance in space. A realization of the three relational categories of substance, causality, and community, which pertain to anything that exists in space and time in general, without adding any further empirical concept. And therefore, they instantiate, since they instantiate the relational categories, they instantiate the three analogies of experience formulated in the first critique. Number 2 in your handout shows the same thing you have here, namely those three laws of mechanics. These same laws, as suggested, of mechanics, belong to what Kant calls pure natural science, and accordingly they are, for Kant, synthetic a priori truths. In the preface to the Metaphysical Foundations, however, that's number 3 on your handout, but it's exactly this, Kant carefully distinguishes between pure and proper natural science. Proper natural science is the broader concept, containing pure natural science as a part, but also containing particular empirical causal laws, such as, paradigmatically, I think, and we'll see reason to believe that in a moment, Newton's law of universal gravitation, which are not strictly synthetic a priori, but nonetheless count as necessary for Kant in the sense of the modal category of necessity. In particular, the law of universal gravitation is inferred from Kepler's so far merely inductive rules by geometry and the three laws of mechanics. It now counts as necessary and universally valid as an empirical law of nature. And here he clearly says later in the dynamics that even that law is derived empirically, but it's not merely inductive, it derives in a way that involves some stronger type of determination, which has yet to be explained. The necessity here is what Kant calls material necessity, that is, causal necessity in the postulates of empirical thought which come under modality. And in the corresponding chapter of the Metaphysical Foundations on phenomenology, Kant sketches a three-stage constructive procedure by which we move from rectilinear motion, taken to be merely possible, to circular motion, taken to be actual, and finally to equal and opposite contrary motions in accordance with the equality of action and reaction, now properly determined, Kant thinks, as necessary. This, as I have argued in detail elsewhere, although I'll tell you more about it later, is how Kant reconstructs Newton's deduction from the phenomena in the early part of Book 3 of the Principia, which, beginning with what Newton calls the phenomena articulated in Kepler's laws, concludes with the law of universal gravitation, and at the same time, the determination of the center of gravity or center of mass of the solar system, where everything is equal and opposite around it. That's what gives you the true center of motion, according to Newton and Kant, for all the bodies interacting there. And so the question is, what does this deduction from the phenomena mean? The whole 2 lectures are going to be devoted to trying to clarify that. We learn more about the concept of proper natural science following the 4th paragraph of the preface to the Metaphysical Foundations, where we left off, and that was what we already saw in your number 3. The 5th paragraph, that is moving on from there, explains that the pure part of proper natural science consists of 2 further parts. Kant is never satisfied with one distinction. There has to be several subdistinctions, and as we'll see, many more. Further parts. The first is pure rational cognition from mere concepts, or metaphysics, and which grounds its cognition only on the construction of concepts, or mathematics. So a priori metaphysics has those 2 different subparts. He asserts that we must presuppose in the first place metaphysics of nature, and he says, for laws, that is, principles of the necessity of that which belongs to the existence of things, are concerned with a concept that cannot be constructed, since existence cannot be presented a priori in any intuition. And this whole thing is quotation 7. But metaphysics of nature, according to the 6th paragraph, and this I won't show, again consists of 2 further parts. A metaphysics of nature in general, which considers only the pure concepts of the understanding, the categories, and then a special metaphysics of nature, which, for example, considers the empirical concept of matter as a particular instantiation of the pure concepts of the understanding. So we add an empirical concept to the pure categories. There follows a notoriously difficult, even by Kantian standards, 7th paragraph, according to which special, unlike general metaphysics, requires the application of mathematics. The crux of the difficulty in understanding this passage involves the role of mathematical construction. So here it is, where he says, to cognize something a priori means to cognize it from its mere possibility. But the possibility of determinate natural things, that means with empirical concepts, cannot be cognized from their mere concepts, for from these the possibility of the thought that it does not contradict itself can certainly be cognized, but not the possibility of the object as a natural thing in the world that can be given outside the thought as existing. Hence, in order to cognize the possibility of determinate natural things, and thus to cognize them a priori, it is still required that the intuition corresponding to the concept be given a priori. That is, that the concept be constructed, unquote. That's very confusing. Is Kant saying that special metaphysics, in particular the special metaphysics of corporeal nature, proceeds by mathematically constructing its concept of matter in pure intuition? Looks like that. But this cannot be right, for the concept of matter is an empirical concept, not a pure mathematical concept. And so empirical concepts as such cannot be constructed in pure intuition, only mathematical concepts can be. This point is emphasized in the very passage from the preface that we are considering. The possibility that needs to be demonstrated a priori is that of the object of the concept as a natural thing that be given outside the concept as existing. Bold face added by me. And Kant, and that's, And Kant has initiated this discussion by explaining the need to begin with metaphysics of nature as opposed to mathematics, that was question 7, which I'll show you again, because existence is a concept that cannot be constructed, and that's why metaphysics won't work, and we need metaphysics rather than mathematics. Moreover, according to Kant's discussion of the analogies of experience in the first critique, the general metaphysical principles governing the existence of things are precisely these 3 analogies, which have to do with the existence of appearances in time, and they have to do with the magnitude of existence, duration, the series of events in time as a successive set of things, and finally the relation to time as a totality of all existence simultaneously. So Kant is not saying that the empirical concept of matter can be constructed in pure intuition, independently of both general metaphysics and experience. The point, rather, is that assuming general metaphysics as our background, we must articulate the empirical concept of matter as an instantiation of the categories of the understanding. And this now must be a mathematical instantiation in particular of the categories of substance, causality, and community. Thus, the most important principle of the special metaphysics of corporeal nature, again, are Kant's 3 laws of mechanics, which instantiate the corresponding categories, substance, causality, community, by applying mathematics to the empirical concept of matter and thereby articulating this concept in a certain precise mathematical way. We thereby obtain a mathematically precise notion of quantity of matter, and thus quantity of substance in this case, a precise notion of force or causal action, governed by the law of inertia, and a precise notion of mutual action or interaction, governed by action equals reaction. These 3 laws are then especially important for the concept of proper natural science, I'm repeating again, in Kant, because they then enable a deduction from the phenomena of the law of universal gravitation from Kepler's rules, or Kepler's laws as we call them. And what Kant says in the immediately following paragraph of the preface provides further confirmation of the paradigmatic status of the law of gravitation by contrasting the application of mathematics in the derivation of this law. Has to be attraction or repulsion. There has to be a law in terms of distances and so forth, which is certainly not possible, at least not yet, in the case of chemistry. That's just why chemistry cannot be a proper natural science. It's not like the law of universal gravitation. It is no wonder, then, that Kant proposes precisely these laws of mechanics in the introduction to the 1787 edition of the Critique. We already saw that, as indisputable examples of synthetic a priori propositions of pure natural science. It is also no wonder that, when discussing the a priori concepts of substance, causality, action, and force in the second analogy, Kant appeals to the example of moving forces to provide the particular content of an alteration of state. And he says here, your number 11 is in front of you. For this, that is the content of the state, to know that, acquaintance with actual forces is required, which can only be given empirically, e.g. the moving forces, or what is the same, certain successive appearances as motion which indicate such forces, unquote. And since these forces give rise to law-governed motions, accelerations, conceived as alterations of state, F equals ma, the law of inertia is also necessarily involved. And the footnote at the very end stresses that what Kant means here in this example is state changes only when the motion changes, not when it stays the same. In the case of such forces, moving forces, the law of inertia, Kant's second law of mechanics, mediates rigorous mathematical arguments by which mathematical properties of forces can be inferred from the mathematical properties of the corresponding motions. As, for example, in the very first two propositions of the Principia, where here we see a body acting under a centripetal force toward the center S. We imagine that in equal times there is some force that is pushing us in that direction because it's centripetal. And the distances are not equal, but then by the geometry of these Euclidean triangles, the areas of the triangles are going to be equal, and that's Kepler's area law. Conversely, if you start with an orbit satisfying Kepler's area law, you can infer that there is a centripetal force directed toward a center, a focus, whatever it might be. That's just the first step in Newton's deduction from the phenomenon. Okay. Proper natural science for Kant appears therefore to be confined to the sciences of moving forces, as paradigmatically exemplified by the Newtonian theory of universal gravitation. Where a supposed science of nature does not rest on such a basis, at least not yet, as in chemistry, as we saw, it cannot yet be a science properly speaking, but rests merely, as Kant says, on empirical principles. While in the case of Kepler and Newton, there certainly are empirical principles, namely the Kepler laws that we start with, but there's also geometry and, most importantly, the three laws of mechanics, which mediate the inference. That's supposed to be the extra kicker. So it appears, unfortunately, that very few of the phenomena of nature can actually be accounted for within proper natural science in Kant's rather strict sense. What then is to be done? Here Kant introduces one of his most central distinctions, the distinction between constitutive principles of the understanding, I'll just stay here, and regulative principles of reason, which do not relate so directly to spatiotemporal intuition. So constitutive principles are necessarily instantiated in spatiotemporal intuition, not so for ideas of reason, which cannot be actually instantiated in any experience that is precisely instantiated. The pure concepts of the understanding have what Kant calls schemata, by means of which they can be instantiated in the realm of spatiotemporal objects of experience, substance in terms of permanence over time, causality in terms of succession in time, and so forth. But this is never possible in the case of what Kant calls ideas of reason. In particular, the idea of the complete systematic unity of all the empirical laws of nature, an ideal state of affairs in which all such laws would somehow be grounded in the constitutive principles of the understanding, can never actually be instantiated in our experience, but only approximated step by step without ever reaching its goal. Okay. Thus, while the metaphysical foundations of natural science studies one precise mathematical instantiation of the categories, the theory of universal gravitation as rigorously articulated, et cetera, by Newton, it by no means straightforwardly extends to the more empirical sciences like chemistry. It is no wonder, then, that Kant treats the contemporaneous chemistry with which he was familiar at the time of the metaphysical foundations and the first critique, even the second edition, as rationally organized instead by the purely regulative use of reason via the idea of complete systematic unity. Kant makes it clear in the preface to the second edition of the Critique that the chemistry he has in mind is Georg Stahl's highly sophisticated form of phlogistic chemistry. Who knew that phlogiston theory could be so sophisticated? But it was. Some of the details of which then appear as central examples of the regulative use of reason in the appendix to the dialectic in both editions of the Critique. For those of you who are interested, you can find further discussion of Stahlian chemistry in relation to these passages from the Critique, analogous passages taken from Kant's lectures on physics from the time, and discussions of chemistry in the dynamics chapter of the Metaphysical Foundations in my Kant's Construction of Nature, section 20. And that's only a very small section of a huge, horrible 600-page volume. Okay. Not horrible, it's actually beautiful, but it's long. In the case of biology, however, the situation is significantly different. For the very way in which Kant understands the law of inertia, here's the statement of the law and then some comments about it, takes matter as such to be essentially lifeless. That he takes to be the heart and kernel of the law of inertia. Biology therefore requires a further rethinking of the Kantian cognitive faculties, and Kant only reaches a successful conclusion by his lights in the Critique of the Power of Judgment, 1790, where a new a priori principle, that of purposiveness, Zweckmäßigkeit, governs a new a priori faculty, that of specifically reflecting, as opposed to determining judgment. Reflecting is the bottom up, where you ascend from the particular to the universal. Determining is the other way around. But now this is a new faculty with its own a priori principle. The upshot is that the nature and generation of living organic matter, for Kant, cannot be explained mechanically. That is, by mechanical moving forces. That is, by any proper natural science. There can never be a Newton, Kant maintains throughout his career, who could explain the nature and generation of even a single blade of grass. Okay. But now the prospects for Kantian philosophy of natural science appear dire indeed. Proper natural science appears so severely limited that fully objective cognition of nature, as Kant understands it, is simply not possible for most of the phenomena of nature. The generation of natural philosophers who succeeded Kant and were inspired by his metaphysical foundations thought they had found a way out, with reason. These, of course, were the Naturphilosophie, and they were led by our friend Friedrich Schelling, who we already correctly identified. For Schelling, transcendental philosophy, the story of how human reason successively approximates to a more and more adequate picture of nature and of reality more generally, has a necessary counterpart or dual, as it were, in Naturphilosophie, the story of how nature itself successively unfolds or dialectically evolves from the dead or inert matter considered in statics and mechanics to the essentially dynamical forms of interaction considered in chemistry, and finally to the living or organic matter considered in biology, and actually even further. Since nature, on this view, dialectically unfolds or successively evolves in a way that precisely mirrors the evolution or development of our rational conception of nature, and of course vice versa, it follows that there is no possible skeptical gap between nature itself and our conception of it. Or, in Kantian terminology, between the constitutive domain of the understanding and the merely regulative domain of reason and reflective judgment. All of the phenomena of nature, including in particular both chemical and biological phenomena, are rationally or objectively grounded in the same way. The key to Schelling's conception is a dialectical extension and elaboration of Kant's dynamical theory of matter in the Metaphysical Foundations, according to which the fundamental property of filling a space to a determinate degree results from a balance or equilibrium between the two fundamental forces of attraction and repulsion. This is just Kant's Metaphysical Foundations. Everybody was reading Kant's Metaphysical Foundations, all the Naturphilosophie at the time. Even Helmholtz was reading it. Even Hertz was reading it. Okay. From Schelling's point of view, this theory of the most general properties of all matters as such, which embraces therefore even the dead or inert matter considered in statics and mechanics, has already introduced an essentially dialectical and evolutionary element into nature, a Stufenfolge, which embraces therefore even the dead or inert matter considered in statics and mechanics. It's already introduced this insofar as the dynamical constitution of matter in general proceeds from the positive reality of expansive force, repulsion, through the negative reality of contractive force, attraction, to the limitation or balance of the two in a state of equilibrium. Yet this equilibrium for Schelling is only a temporary first step, for we now know, as Kant himself did not, that chemistry, that is the new turn-of-the-century electrochemistry, can be dynamically grounded by a dialectical continuation or extension of the same progression as we proceed more specifically from the magnetic through the electrical, static electricity, to the chemical or galvanic current electricity and its relation to chemistry, of the basic or original dynamical process grounded in the fundamental forces of attraction and repulsion. And once we have gone this far, it is then a very short step, particularly in view of the newly discovered parallel interconnections among electrical, galvanic, and biological phenomena, such as the discovery by Galvani that a severed frog's leg will jump when stimulated by an electric current, and in general, we are coming to understand the electrical nature of nervous signals, to view biology too as a further dialectical continuation of the same dynamical process. Biology too can be a science, a proper science. For all natural rational science, as Kant did not see, is grounded in a single dynamical evolutionary dialectical progression. The whole of nature, in this sense, is at once both rational and alive, and quotations 16, 17, and 18, which are long except for the very last one. You see what Schelling has to say about that. I'm just going to skip over it now, but if you want to take a look at it, don't look for too long, because I'm going on. Schelling's entrancing vision, now I'm going to show you something else, is fueled by a number, which will show you that there's actually some real science here that they're dealing with. Schelling's entrancing vision is fueled by a number of dramatic new discoveries in the new electrochemistry. In particular, the invention of the voltaic pile, 1800, had led to the discovery of current electricity or galvanism. And current electricity, in turn, had led to the discovery of the electrolytic decomposition of water, whereby oxygen and hydrogen separate out from the water and accumulate respectively at the positive and negative poles, inducing the electric current. That's what you see. That's a modern picture. Oxygen and hydrogen were thereby associated with negative and positive electricity, respectively, and this suggested an especially close link between chemical forces and the fundamental, between electrical forces and the fundamental chemical forces involved in combustion. Schelling, along with many other researchers of the time, took this as evidence for the electrical nature of chemical affinities quite generally. Indeed, a particularly important electrochemical researcher of the time was Johann Ritter, who was actually at Königsberg, although much younger than Kant, who was also a Naturphilosoph and admirer of Schelling. Ritter, in fact, was the first experimentally to demonstrate that the volume of hydrogen gas produced by electrolysis is twice that of oxygen gas. Yet the most important Schellingian researcher of all was Hans Christian Ørsted, a close friend and collaborator of Ritter's, who had discovered electromagnetism in 1820, directly inspired by Schelling's idea that the basic or original form of the dynamical process is further differentiated at the level following Kant's into magnetism, electricity, and chemical force. So here we see electromagnetism, of course, means that if you have an electric current flowing, it generates a magnetic field, and Oersted knew that it satisfied the so-called right-hand rule, where if you're pointing in the distance of the current with your right thumb up, then the thing is going to be deflected the way this last piece is pointing. That's the right-hand rule. And as suggested, once electrochemical forces are included, then it's a very short step to biological ones. And indeed, Schelling and the Naturphilosophie thought, well, then it's not too far to consciousness and specifically human experience either. Okay. That the whole of nature in this sense is at once both rational and alive, insofar as it involves a dialectical progression from the most primitive to the most sophisticated forms of natural products, depends on Schelling's rejection, in accordance with virtually all of post-Kantian German idealism, of Kant's fundamental cognitive dichotomies between constitutive and regulative principles, the faculties of understanding and reason, and in the end, the distinction between sensibility and understanding as well. Kant's conception of theoretical knowledge, by contrast, involves precisely these dichotomies between sensibility and understanding, understanding and reason, mechanism and teleology. It rests in particular on a dichotomous balance of opposing elements, a positive account of the possibility of such knowledge, together with a negative account of its limits. And the positive account of the knowledge in question requires that it also be limited within certain boundaries. Thus, in the transcendental deduction, a priori intellectual knowledge of all appearances that may be presented to our senses by the understanding is possible in virtue of the schematization of the understanding within the forms of our a priori intuition, forms of sensibility. That it is only possible in virtue of such schematism, however, limits our theoretical knowledge to what may be given to our senses in space and time. Moreover, since what Kant calls proper natural science is necessarily mathematical, it requires a further schematization or realization of our understanding in terms of mechanical moving forces within specifically corporeal or material nature in space and time, essentially involving the empirical concept of matter. Yet this kind of science, although undeniably paradigmatic for Kant from a theoretical point of view, has its own necessary limitations as well, which in turn open the way for a non-mechanical, teleological understanding of nature in biology, although it's now purely regulative. And the reason for Kant that this is an advantage rather than a disadvantage is that Kant gives a certain priority to the demands of morality, that is pure practical reason, over everything else. Because of the necessary limitations of a fundamentally mathematical understanding of nature, which is the only kind of understanding that allows us, in principle, to predict the course of future events, we are then free to consider the future of life on Earth as rationally comprehensible only from a teleological point of view. We have no choice in particular but to view human history from the perspective of a teleological regulative ideal, connected to the realization of the kingdom of ends here on the surface of the earth. For the end in question, the pursuit of the highest good, is unconditionally commanded by morality. There is no practicable way further to address the more general issues between Kant and post-Kantian German idealism within the scope of these lectures, or actually a long time. But we can discuss why and how the further development of the physical sciences in the 19th century, and also that of the life sciences, including aspects of psychology, took a completely different direction from that is envisaged by Naturphilosophie. Many of these developments, moreover, were initiated by Hermann von Helmholtz in the context of a direct attack on what he took to be the Naturphilosophie of Schelling and Hegel. He liked Fichte, by the way. There was some Fichte who was a friend of Helmholtz's father, yes? But he didn't like Schelling and Hegel. Together with a call for a return to Kant. Kant's more Newtonian conception of the fundamental forces of nature thereby appeared now to be vindicated, at least in the physical sciences, and maybe the biological too, over the living forces of the Naturphilosophie. So I shall now proceed, after a break, to Helmholtz's criticism of an alternative to Naturphilosophie, and then briefly to the development of 19th century scientific philosophy from Helmholtz to Einstein. Not bad. Not bad. Less than 40 minutes. Yes.
Very good. So we'll we'll take 10 to 15 minutes of questions.
Did Kant reject the phlogiston theory?
Sorry?
Did Kant reject phlogiston theory?
He did embrace Lavoisier starting around 1790, which is really when it got more publicized in Germany. That has to do with his opus posthumum that was published. So in the 90s, he came better and better acquainted with Lavoisier's chemistry, and at that point he says chemistry is a science.
Yes, thank you for a quick and profound talk. I have a question that I would like to take you back to what you said at the very beginning about the relation between general metaphysics and special metaphysics for Kant. So the distinction he inherits from Wolffian metaphysicians, and there it means something quite different from what he makes of it. Namely, it was general metaphysics, namely ontology, and then special metaphysics, namely a priori theory of the soul and of the world and of God.
So metaphysics of nature would be part of special, yes?
Well, they had cosmology, they didn't have nature. So that's my question, actually. So it looks to me like after the critique, there is really no such thing as general metaphysics anymore, in the sense in which general metaphysics was ontology, and Kant says, the famous passage from the critique, now the proud name of ontology should leave the place to an analytic of the pure concepts of the understanding, among other things, the analogies of experience, and as you said, the axioms of intuition, the anticipation of perception. And the only special metaphysics that remains is not rational psychology, rational cosmology, rational theology, but metaphysics of nature,
yes,
and metaphysics of morals, each of
yes,
which
yes,
presupposes an empirical concept, the concept of matter, and the concept of person, each of which has an a priori component, but is an empirical concept. And so I was wondering whether that doesn't give a slightly different sort of frame to what, no more ontology, analytic of concepts. And then once you have that analytic of concepts, import something empirical and see how you should think about it. And of course, the real question is, and so what is the fate of that analytic of concept? Anyway, I was wondering what you think of this way of reframing the whole question of general metaphysics and then special metaphysics.
I like it, and I like very much stressing that there's metaphysics of nature and metaphysics of morals.
Yeah.
However, in one of your favorite books, he uses ontology again. In section 5 of the introduction to the critique of the power of judgment, he again gives this difference between the two. He calls a transcendental principle and a metaphysical principle. The transcendental principles are the categories which he now calls pure ontological concepts, like substance and causality, as opposed to concepts like matter and
Right.
so there's still ontology there, even in 1790. It's not saying, well, now I believe that there's ontology. Just but he uses that contrast between. It's not general and special. It's transcendental principles and metaphysical principles. And the metaphysical principles are like in the metaphysical foundations. The transcendental principles are like the principles in the first critique, and those he calls. And the concepts, the categories he calls general ontological concepts.
So the question is this ontology reinterpreted in terms of a transcendental philosophy or actual ontology? Anyway, thank you.
Yeah, I have a question. You describe Kant as saying that it's by applying mathematics to the empirical concept of matter, we thereby get a conception of the quantity of matter, and I suppose magnitudes more generally, Newtonian mechanics. In giving that formulation, Kant is in effect rejecting a conception of magnitudes in which they don't intrinsically involve numbers, an older conception, the kind of thing you get in Eudoxus and Euclid. One question is historical, another is essentially philosophical. Historical question is, do you have views about why he went that route? And secondly, if you don't go that route, if mathematics isn't, if, for example, the real numbers aren't involved intrinsically in the nature of magnitudes, but you do something more in the Eudoxus, Euclid, Dana, Scott style of fashion, Then what's happened to the a priori element? Does the a priori element come via the axioms governing these magnitudes? I'd like to hear reflections anyway.
Good question. Now, Newton, you may recall, actually doesn't use real numbers, he uses ratios.
He uses ratios. Absolutely,
There
that's
is
the Euclidean
there
thing.
is no number, but it's the constant.
Absolutely, yeah. Yeah.
So Kant is perfectly happy with that. He's familiar with the Eudoxian theory. So that for him would be, and his axioms would be a theory of magnitude in his sense. And there's a lot to say
Right.
with that. So the idea that you would, arbitrarily pick a standard and then get particular real numbers doesn't play any particular role for Kant. It's just that there are ratios, and of course the ratios have numerical features.
Right, but the magnitudes themselves may have real values. And so the conception of the range of magnitudes that you need in Newtonian physics would be wider than anything just got by the natural numbers of the ratio.
You have an equivalence class of same
Uh,
ratios.
by the same
which
ratio, yeah.
does the job of
Right.
the real number.
Right. Yeah, so the part of, so suppose we take Kant as being entirely happy with that aspect of Newton, a kind of Eudoxian version of Newton. Then what's really being drawn on there? It's just the natural numbers in giving notion of extensive magnitude, or?
Yeah, there's certainly the natural numbers, the rationals, and arbitrary ratios, even if those are not commensurable ratios.
Right, but those could be explained in terms of magnitudes if you have a different direction of explanation. I mean, so you can imagine somebody who comes along and says, yes, you need this general notion of magnitude, you need the natural numbers perhaps in explaining what an extensive magnitude is, but then maybe you could introduce the real numbers then as certain kinds of ratios. But
He wouldn't be
they
unhappy with that. He's
right.
aware of that in the contemporary algebra. He doesn't have a dogmatic view about it.
Right.
I think when he talks about algebra, he has three things in mind. One would be the Eudoxian theory. The other would be the theory of equations. And the third would be some kind of modern use of real numbers that people were doing in physics.
Yeah. So what he
Galileo,
okay.
Newton, and many people, the theory of ratios was, as it were, the rigorous story of what they were doing.
Mhm.
And it didn't really hurt the power of it, up to a point.
Okay.
One last one.
You mentioned the opus posthumum. Kant, at that point, agrees chemistry is a science. Question is, does he reject the regulative constitutive divide in that work definitively or not?
In the opus posthumum?
Yeah.
I wouldn't say he does it definitively. One thing he does do, he compromises it, though. So the way I mean, it's very controversial and very difficult, as you know. But he, in fact, I think I know who you are. But there is one place where the distinction becomes compromised, and that is he has this so-called ether deduction, and which is going to be it's going to be a version of the matter of heat, but it's also going to be the medium for all forces, and it's also going to be what realizes it's space realized. Okay, and as realized space, it is constitutive. But as the principle of the unity of all forces of nature, it's regulative. So it is a representation that is both constitutive and regulative. That doesn't mean he's going to completely say there is no distinction, because that would mean no more distinction between sensibility and understanding, and that wouldn't be Kant. So that's how I think of it, for whatever it's worth. Tim had a question, and
Tim has a question. Well,
since we do have a little time, I think we should.
I'll make it quick. So I've always had a hard time understanding really what the project of philosophy of nature is after Kant, in Schelling and Hegel, especially in Kant, what it's actually trying to do. And if I've understood you correctly, what you're suggesting is really the project is should be understood as a continuation of the third critique and the part on teleology, where, just to put it very generally, reflections on the nature of science, in this case the nature of biology, are part and parcel of an account of how, let's just say, the highest good gets realized. And that might be a way of thinking, or helping me to think more about what philosophy of nature is in the post-Kantian sense.
I think it's also part of his idea of philosophy of nature, because it's not just the third critique, it's the third, as I read it, the third critique in relation to the metaphysical foundations, because he talks about moving forces and mechanical forces when he's talking about the antinomy. And so really, and for them, for Schelling and the early Hegel, and many of them, the Metaphysische Anfangsgründe and the third critique are intersecting in the philosophy of nature. But the philosophical project is to see how scientific knowledge of nature relates to everything else we care about, let's say. And we all would like that. Maybe Tim would.
No. So I guess because we're kind of paused here between the two lectures, I guess I'd just like to know how you think about what you're doing in this sense. So of course, there's an interesting question of what Kant had in mind, of trying to understand what he was thinking. And how he was arguing and so on, which is quite a task to get straight.
Yeah, we have evidence for that at least.
Yeah, and but there's a certain sense in which the actual history of science was as unkind to Kant as it could conceivably be, right? Because you say he wanted to show how we know a priori that space is Euclidean, and today we say, sorry, we have to know a priori that there will be a rigorous causal theory, and you say, sorry, right? You go, relativity, right? Quantum mechanics, even right now, I'm talking to people about whether there's any conservation of energy, whether anything's conserved. Certainly not a requirement of science or our understanding of the world scientifically that there be any conservation laws. So, all of the very particular doctrines that he was trying to establish as a priori synthetic appear to be just false. And if you think that, then you think, well, what we're doing here is a kind of, autopsy of a theory that certainly, a project that died multiple times in gruesome ways at the hands of science. But that doesn't seem to be what we're going to do next time.
What's the problem, Tim?
Well,
Okay.
So I'm just wondering how you think about how you think about this.
I'll tell you so you know what to expect. Now, as a matter of fact, Helmholtz tries to keep aspects of Kant. Poincaré tries to keep aspects of Kant. Kuhn tries to keep aspects of Kant. Ernst Cassirer, all the way for general relativity, says no problem, we can generalize things, and the heart of the Kantian theory can be kept, the idealism can be kept, blah, 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 blah. So there is an ongoing project by serious people who are very smart and who know the science and who know the philosophy, who are saying, of course we can't have what Kant said we would have. No Newton, no Euclid. We need to somehow generalize, relativize, and do something where we're still doing justice to the idea that the mind has to bring some constitutive principles to nature in order to have a science at all. Now, those principles may change, and they do change, but nevertheless, we want to be able to identify them and have a story about them. And for the next, actually, you're going to see. So the point is, a lot of very smart people tried to keep doing that. At the very end, I will give you my story, and you can then tell me why it fails to. I won't have anything much to say about quantum mechanics. So.
Well, that's a very good segue for the next part.
Okay, well, thank you. I'm encouraged that this might be possible to do. Okay, so now we move on to the next one. Helmholtz first came to be identified as one of the leaders of the emerging back to Kant movement for a scientific philosophy. That is, it was the Naturphilosophie who were the bad guys now, so we have to go back to Kant and away from metaphysics. In his celebrated address, that is Helmholtz's, On Human Vision, delivered at the dedication of a monument to Kant in Königsberg in 1855, and this became one of the primary intellectual models of this movement, which then became known as neo-Kantianism in its many forms. Helmholtz began by asking himself, on behalf of his audience, why a natural scientist like himself, at the time a professor of physiology at Königsberg, is speaking in honor of a philosopher. This question only arises, Helmholtz says, because of the current climate of enmity and mutual distrust between the two fields, a climate which is due, in Helmholtz's opinion, to the speculative system of Naturphilosophie that Schelling and Hegel had erected independently of, and even in open hostility towards, the positive results of the natural sciences. What Helmholtz is now recommending, by contrast, is a return to the close cooperation between the two fields exemplified in the work of Kant, who himself made significant contributions to science in his nebular hypothesis of 1755. And in general, Kant, Helmholtz says, stood in relation to the natural sciences, of course, of his time, together with the natural scientists on precisely the same fundamental principles. Now, the charge that Helmholtz levels against Naturphilosophie is fundamentally unfair, insofar as the latter, Naturphilosophie, was a reasonable and responsible response, especially against the background of the metaphysical foundations, to the new developments in electrochemistry and electromagnetism, which were real science. Yet Helmholtz had important new weapons up his sleeve, beginning with his formulation of the principle of the conservation of energy in 1847. And here it's called force, Kraft. In the introduction to this work, Helmholtz describes, I think I've not gone quite far enough. Okay. I just note here that there's a difference between the first edition of 1847 and the second of 1881, because there's going to be a significant change of view there, which I will come to. Okay. So in the introduction to this work, Helmholtz describes, quote, the ultimate and proper goal of the physical natural sciences as such, and he includes biology here, physiology, as beginning with an experiential part where one seeks to describe the individual natural processes by general rules, which are obviously nothing but universal generic concepts through which all of the appearances belonging thereto are comprehended, Helmholtz's words, and proceeding to what he calls a theoretical part, which seeks, by contrast, to find the unknown causes of the processes from their visible effects. It seeks to conceptualize them in accordance with the law of causality, unquote. This procedure aims eventually to discover the ultimate unalterable causes, as he puts it, lying at the basis of all appearances. Now, in number 2 of the handout, you see, in large detail that and his language. I'm not going to read it, but you have it there if you want to talk about it later. But that's the idea of the introduction. And the possibility of reducing all of the appearances of nature to this basis, the ultimate, unobservable, unalterable causes, is, in accordance with the law of causality, according to Helmholtz, quote, the condition for the complete conceptualizability of nature. Thus, when Helmholtz, in his 1855 lecture on human vision, says that Kant stood, quote, together with the natural scientists on precisely the same fundamental principles, unquote, what he has primarily in mind is Kant's formulation of the principle of causality as he understands it. That is, Helmholtz understands it. And the salience of Kant's formulation becomes clearer when we note that the ultimate unalterable causes mentioned in the above quotation from the 1847 monograph turn out to comprise a system of masses interacting with one another solely through time-independent, that is, constant or unalterable, central forces of attraction and repulsion, depending only on the distance between them. That's what Kant says in the Metaphysical Foundations. Helmholtz virtually quotes from the Metaphysical Foundations at that point. The main burden of the monograph that follows is then to contribute to this program by showing that the phenomenological principle of the conservation of energy, which expresses the transformability of different forms of energy into one another as a quantitative conservation principle, is equivalent to the theoretical principle that all actions in nature are in fact representable by ultimate forces of attraction and repulsion in this way. The principle of the conservation of energy for him is thereby shown to involve a more specific realization of Kant's general principle of causality, the second analogy, corresponding in this respect to Kant's own more specific realization of the transcendental principles of the understanding in the Metaphysical Foundations of Natural Science. So it's stronger than the first critique view. For Helmholtz, accordingly, all the manifold phenomena of nature, mechanical, thermal, chemical, electromagnetic, and biological, among which we see energy transferred, or we believe which, and in which we see the total quantity of energy, we believe that, conserved, are ultimately representable by an underlying system of invisible, unalterable masses governed by fundamental forces of attraction and repulsion, closely modeled on Kant's dynamical theory of matter. Helmholtz is thereby in a position to use Kant's theory to make a number of telling objections against Schelling's dialectical extension of it. First, and most importantly, it follows that Kant's original theory on this view is entirely capable in principle of comprehending all the new discoveries appealed to by Schelling. That's what Helmholtz thinks. Second, and as a corollary, there is no need to incorporate life or any vital principle into the fundamental forces of matter. On the contrary, by adopting attractive and repulsive forces, mechanical moving forces, as fundamental, we thereby attain a unity of all the forces and powers of nature that is completely different in kind from the organic or teleological in unity envisioned by Naturphilosophie. Third, and finally, no essentially non-Newtonian physical principles are required after all, for Newtonian central forces of attraction and repulsion, obeying only the principles of Newtonian mechanics, suffice, according to the first edition of 1847, to explain all the phenomena governed by the new principle of the conservation of energy. And he tries to prove that there's an equivalence between the phenomenological principle and this very strong constraint, which of course isn't true. In this context, Helmholtz takes the main point of Kant's principle of causality to be that of licensing an inference from the observable phenomena or appearances to the unknown causes of these visible effects, an inference from the observable phenomena to their unobservable cause. However, by the time that he revises and adds supplementary notes to his monograph in 1881, Helmholtz has clearly abandoned this view. In the first note in particular, Helmholtz corrects the above-cited sentence where the law of causality is said to lead us to ultimate unalterable causes from their visible effects as follows. The philosophical discussion in the introduction is more strongly influenced by Kant's epistemological views than I would now like to recognize as correct. That is his reading of the principle of causality. I only made it clear to myself later, Helmholtz continues, that the principle of causality is actually nothing other than the presupposition of the law-likeness of all the appearances of nature. Unquote. The principle of causality can no longer serve as a justification for postulating unknown, invisible objects behind the observable appearances. Rather, law-likeness is now a fundamental principle governing, we hope, the appearances or phenomena themselves. This shift in Helmholtz's thinking away from his earlier commitment to the mechanical or mechanistic framework of the metaphysical foundations was connected to his evolving understanding of electromagnetism. It was clear from the beginning that electrical, magnetic, and electrochemical forces all satisfy the conservation of energy as a phenomenological principle. In particular, the relationship between galvanic cells, batteries, and electrolytic cells, used to separate oxygen from hydrogen from water, for example, was fundamentally clarified by energetic considerations. The former involved the conversion of chemical energy into electrical energy, while the latter precisely the reverse. This, of course, is a modern picture, which even shows the little electrons there. But of course, they didn't have those at the time. I mean, they were there at the time, but they didn't know about it. Okay. But the point is there's a symmetry between the two, whether you have electrons or not. And this further suggested against Naturphilosophie that the relations among magnetic, electrical, and galvanic phenomena did not have the unidirectional teleological character prized by the Naturphilosophen. Moreover, the discovery by Michael Faraday of magnetic induction, 1831, showed that an analogous symmetrical relationship holds between electricity and magnetism. Wait a second here. Not so fast. Yeah. Not only does an electric current induce a magnetic field, as had been discovered by Ørsted in 1920, a moving magnetic field, that's in the Faraday case, also induces an electric current. But these phenomena, taken together, turn out to be very difficult and ultimately impossible to accommodate with the Newtonian action at distance forces embraced by Kant, and instead eventually led to the space and time dependent electromagnetic fields of James Clerk Maxwell, propagating through space with the constant velocity of light. Nevertheless, Maxwell's theory was still essentially Newtonian in its mathematical methodology, which purely as methodology is already in conflict with Naturphilosophie. So just to back up and clarify that, by 1881, Helmholtz knows that he doesn't have a theorem that says that from the phenomenological conservation of energy, you can derive these unalterable forces, these central forces, right? And therefore you rule out something like Maxwell's theory. Indeed, he comes to understand Maxwell's theory, and he tries to revise his view in the second edition, not to embrace this idea of continuous propagation, which actually wasn't clearly established until Hertz, but a general kind of action and potential view. I'll talk about this in the last lecture, which would be, he hoped, consistent with either a kind of action at a distance theory like Ampere or Weber, but also consistent with Maxwell. And even Hertz tried to say that those things were all consistent and have a general principle that he could derive each one from the other. It was by trying to do that and realizing that this was actually not possible that he then realized, well, we have to show that Maxwell's theory is right, or we want to show that because there really is this propagation, which is shown by his radio wave experiments. Okay, so we'll get to that in the last lecture. But what I mean by the Newtonian mathematical method is that we can treat the electromagnetic field as basically as a purely mathematical quantity, just like in the case of Newton's gravitational force, which is, of course, an action at a distance force, but that doesn't matter. This is still an abstract measurable magnitude, at least if you follow the theory just as Maxwell's equation. And so Newton's method still seems to be present. Okay, and this will be clarified later, I hope. This shift in Helmholtz's thinking away from ultimate unalterable causes, that is, action at distance forces, was also mediated by the further articulation of what Helmholtz called an empiricist theory of space perception in his monumental Handbook of Physiological Optics, completed in 1867. The basic idea is that our ability to see objects around us in space perception, as localized at particular places, is not an innate capacity of either our consciousness or our nervous apparatus. Rather, this ability is gradually learned or acquired for Helmholtz, as we acquire our native language, for example, by a process of what he calls unconscious inductive inferences, based on regularities or associations among our sensations. The sensations you can think of as non-spatial point-like flashes with different colors, say. For example, my ability to localize a perceived table, let's call it a lectern, in three-dimensional space is in no way directly given by simple visual or tactual sensations. It rather requires unconscious knowledge of a large number of regularities among such sensations generated as I move around the table, just to show you that I can do it. And my sensations are indeed changing according to the laws of perspective. And I can walk into the table and feel that it is solid and so forth. So it's those regularities, he says, which gives us our conception of the location of an object in space. And indeed, it's what gives us the representation of space in the first place, since it isn't just given in a flash, as he says, a lightning flash. Okay. In this sense, the ability to see objects in space is primarily an affair of the understanding. And as Helmholtz says, quote, the fundamental principle of the empiricist view, as opposed to the nativist view, it's not rationalism, it's nativism, is that sensations are signs for our consciousness, where learning to understand their meaning is left to our understanding by grasping the general laws, that is, the comprehending them conceptually. This work on the psychophysiology of space perception was closely connected with Helmholtz's mathematical contributions to the foundations of geometry, developed mainly in the years 1866 to 70, which resulted in what we now know as the Helmholtz-Lie theorem. And it paved the way for Helmholtz's fundamental transformation of the Kantian doctrine of pure spatiotemporal intuition in his work called The Facts in Perception, first presented as a public lecture in 1878. So we add that to our list. For the upshot of this theorem for Helmholtz is that the same regularities in our sensations, on the basis of which we acquire the ability to localize objects in space, also give rise to the representation of space itself, as I said, but now he thinks he has a mathematical construction of that. The voluntary actions of our bodies that allow us to localize objects by moving towards, away, and around them also make possible a precise mathematical construction of the very three-dimensional space within which this process of localization takes place. In this way, space does not serve as the locus of mind-independent objects, existing behind the veil of perception, as it were, but rather as what Helmholtz calls a subjective form of intuition, and he means in the sense of Kant, so that, quote, space will also appear to us sensibly, clothed with the qualities of our sensations of motion, as that through which we move, through which we can gaze forth. It is thus, as he continues, the necessary form of our external, that is spatial intuition, because we comprehend precisely that which we observe as spatially determined as the external world. Unquote. The world of objects in space is truly external only in the sense of being spatial, and space itself is a construction erected entirely on the basis of our inductively acquired ability perceptually to what we call localizing objects, that is, grasping certain regularities. Helmholtz's mathematical work was directly inspired by Bernhard Riemann's creation of what we now call the general theory of manifolds in his Habilitationsvortrag of 1854 on the hypotheses which lie at the basis of geometry. Helmholtz's goal in his own essay on the facts that lie on the basis of geometry, 1868, was to derive Riemann's most important assumption or hypothesis, that the line element or metric is infinitesimally Euclidean, Pythagorean, from what Helmholtz took to be the fundamental facts generating our perceptual intuition of space. Since our representation of space, as explained, arises kinematically from our experience of moving up to, away from, and around the objects thereby localized, the space in question must satisfy a condition of free mobility, permitting arbitrary continuous motions of rigid bodies, and from this condition in turn, we can then derive the Pythagorean form of the line element. Finally, since the Riemannian metric thereby constructed has what we now call a group of rigid motions or isometries, mapping any point onto any other, the only possible geometries that we construct in this way are the three classical geometries of constant curvature: elliptic, constant positive curvature; hyperbolic, constant negative curvature; and Euclidean, constant zero curvature. I must say, though, that that picture of negative curvature isn't really right, because there is no surface embeddable in three-dimensional space which has constant negative curvature, which was proved by Hilbert in his Foundations of Geometry. So that's not really the best picture. A better picture is the Klein model, but I'm not going to bother you with all that right now, because we don't have time. Okay. So, but I will illustrate the difference between constant and variable curvature with this simple example. Constant curvature you have here because the curvature is the same no matter where you are on the surface, but not here with the egg. The egg has a stronger curvature at the sharp end and at the fat end a less smaller curvature, so that you have a triangle, the sum of whose angles is, say, something greater than 180 degrees, and it's at the thin end, and you move it here, it's going to be distorted. It won't keep the same. It won't be congruent to itself when you move it. Okay. Okay. But it now follows for Helmholtz that specifically Euclidean geometry, because we have these three possibilities now, that's what the fact, namely the fact of free mobility, gives us. Specifically, Euclidean geometry is not built into what he takes to be the essential or necessary character of space, given by the condition of free mobility. In particular, it follows from Helmholtz's theory of the origin of our spatial intuition that the particular propositions of Euclidean geometry are by no means necessities of intuition in Kant's sense. For we can now imagine, for example, the series of sensations we would have if we were to find ourselves moving around in a space of constant negative curvature. And such a series of sensations on Helmholtz's theory would constitute an intuition of space. Since the axioms of Euclidean geometry are not built into the most general necessary conditions underlying our spatial intuition and the possibility of measurement, he thinks that Measurement requires free mobility, so the measuring rods have to keep their dimensions as you move them around. Kant's theory of the origin of these axioms in our necessary and transcendental intuition of space is incorrect. Good. And they emerge rather as merely empirical facts about the actual behavior of our measuring instruments. Nevertheless, Kant's insight that space is a subjective form of intuition rather than an ordering of things in themselves existing behind the veil of appearances continues to be correct. For, as Helmholtz conceives it, quote, the most essential features of spatial intuition, including free mobility and therefore constant curvature, are derived from the same original law-like experiences of bodily motion on which our ability to localize objects in space depends. And it follows, just as it did for Kant, that we can now give a solution to what Helmholtz calls the fundamental problem of epistemology, which did not involve a relation of correspondence between our perceptions and truly mind-independent objects existing behind the veil. For that to which our representations finally correspond are law-like patterns taking place within and indeed constituting the space of our form of intuition. And number 6 on your handout is a long thing that I won't read, but there it is if you want to take a look at it. I will show you some other things. In other words, so I will give you in other words what the long thing said. The correspondence of our sensations to enduring external objects in space is now simply equated with their characteristic law-likeness. I had it already. What we can find unambiguously and as fact, as without anything hypothetical, is the law-like in the appearances that is not the possible stuff behind them. This is all controversial, by the way, what I'm saying, as a reading of Helmholtz. So he goes on, from the first step on, when we perceive the objects lingering before us as distributed in space, this perception is the recognition of a law-like connection between our motions and the sensations thereby occurring. Accordingly, Helmholtz formulates the Kantian contrast between appearances and things in themselves, as he now understands it, as a distinction between what he calls the actual, das Wirkliche, and the real, das Reale. Quote, we have in our language a very happy designation for that which influences us, standing behind the change of appearances, namely the actual. Here only the action is expressed. It lacks the secondary reference to enduring existence as substance that the concept of the real, das Reellen, suggests. Okay. Since what stands behind the change of appearances is the enduring existence of law-like relations among our sensations, and as Helmholtz says, quote, I'm not showing this to you, but in the same part of the book, the law-like is thus the essential presupposition for the character of the actual, unquote. It follows that we thereby know the actual, but not the real. I do not need to explain to you that it is a contradiction in terms, that's number 9, but here it is, to represent the real as Kant's thing in itself be a positive determinations, but without taking it up into the form of our representing. So at least we can't call it a substance. This is often discussed, but what we can achieve is an acquaintance with a law-like ordering in the realm of the actual, to be sure, only presented in the sign system of our sense impressions, unquote. This last clause, as we have seen, or at least as I think, does not mean that the sign system of our sense impressions somehow corresponds to a mind-independent realm existing behind the appearances to which it is, say, isomorphic. That's a way to read Helmholtz. For what Helmholtz here calls the realm of the actual, I say, consists precisely of the law-like relationships existing within the appearances themselves and of the Helmholtz part. So we should at least stretch a little bit, take a deep breath, and then we go to Poincaré and Einstein, a shorter but still rather dense. I don't want you to fall asleep before we get to the end. So I guess I have time to go on to the end, and then we'll have the question period. I finally, and more briefly, a little more briefly, turn to the contributions of the great mathematician, mathematical physicist, and scientific philosopher Henri Poincaré, who in several important respects was the most important bridge between Helmholtz and Einstein. Mach is there too, but I didn't even have ambitions to include Mach if it was a whole lecture. In particular, Poincaré himself made very significant contributions to the electrodynamics of moving bodies around the same time as Einstein's publication of the special theory of relativity in 1905, to such an extent, in fact, that there is still an ongoing debate concerning who first discovered this theory. It's not much of a debate anymore, but you still find it. Moreover, Poincaré's articulation of a conventionalist philosophy of geometry also deeply influenced Einstein, as I hope to show, not only in his formulation, Einstein's of special relativity in 1905, but also now considered in relation to the opposing empiricist philosophy of geometry earlier developed by Helmholtz in Einstein's development of the general theory of relativity in the years 1912 to 15. The best known and most influential statement of Poincaré's scientific epistemology, of course, is Science and Hypotheses from 1902, whose subject is mathematics and the mathematical sciences. For it is in precisely these sciences in particular that we meet the centrally important examples of statements that, as he puts it, are only hypotheses in appearance and reduced to definitions or conventions in disguise. That quote I'm not going to show you, but you have it in number 10 of your handout. It's wonderful. He talks about how, well, you can read it yourself. Experience still guides us. It's a prince we have to listen to, but it doesn't compel us. Poincaré concludes his brief introduction by a review of what he calls the series of sciences from arithmetic and geometry to mechanics and experimental physics, beginning with the sciences where free conventions are most evident, where we are dealing with what Poincaré calls frames that we impose upon the world, and concluding with the more physical and empirical sciences. This series or hierarchy of sciences begins with arithmetic, where, according to Poincaré, we find the most characteristic form of mathematical reason, namely reasoning by recurrence or mathematical induction. He thinks that has to be synthetic. This science is synthetic a priori in Kant's sense and is thus a necessary frame we impose on all of our experience. At the next lower level, we find another important frame we impose upon our sense experience, namely the framework of mathematical magnitude comprising the full continuum of real numbers. It is at the following third level, that is geometry, however, that we find the concept of space, a very special example of a three-dimensional mathematical continuum. Here, Poincaré follows Helmholtz in taking the sensory experience in question to be that involved in our experience of bodily motion. The experience for Poincaré, in order to apply mathematics to this intuitive experience, we then need to form a corresponding rigorous concept. And this, for Poincaré, is the concept of a group, a highly idealized description of our actual experience. Let me read that again because it went by. Poincaré follows Helmholtz in taking the sensory experience in question to be that involved in our experience of bodily motion, and he calls that the experience of bodily displacements. Displacements happen when the change in your sensations is correlated with it's correlated with them being reversible by you. I experience a change, but then I can undo it. That's a displacement. If I'm experiencing changes where I can't do that, that's a real change somewhere out there. Okay? In order to apply mathematics to this intuitive experience, we then need to form a corresponding rigorous concept. And this, for Poincaré, is the concept of a group, a highly idealized description of our actual experience. In particular, we assume as an additional idealization that we thereby arrive at a continuous group in the sense of Sophus Lie, where the displacements under consideration are themselves ordered and arranged in a mathematical continuum, in this case, a continuous manifold of 6 dimensions. It now follows by what we can truly call the Helmholtz-Lie theorem. Helmholtz never would have called it that, and he didn't have that result, but he had something that was moving toward it. It now follows by the Helmholtz-Lie theorem that space in this sense has a metrical geometry. And so for Poincaré, we now have the beginnings of an explanation for how we were able to apply the exact science of geometry to our inexact sensory experience. In particular, we now know that the space thereby constructed must have one of the 3 classical geometries of constant curvature. because we have free mobility, elliptic, hyperbolic, or Euclidean. But how do we then know which of these three different cases actually obtains? Helmholtz's answer, roughly and controversially, was that the most essential form of spatial intuition includes only free mobility and thus constant curvature, and therefore that the specifically Euclidean character of physical space, he takes that to be true, is a merely empirical fact about the actual behavior of our measuring instruments as we move from and around in accordance with the condition of free mobility. So you try to construct triangles, you see whether the sum of the angles adds up to 180 degrees or is different. In the latter case, in principle, you will find out that it's non-Euclidean. In this sense, Helmholtz's philosophy of geometry was Kantian, insofar as space indeed has a necessary form expressed in the condition of free mobility. But it was empiricist insofar as which of the three possible geometries of constant curvature obtains is then determined by experience, for example, by measuring the angles of a triangle, etc., like I just said. Poincaré's revolutionary answer, however, was neither Kantian nor empiricist in this sense. The specifically Euclidean form that we impose upon our experience of bodily displacements is neither necessary nor empirically determined, but rather a definition or convention in disguise resulting from the free activity of our mind, but we have to remember those are not completely unconstrained by experience. For in the first place, the group theoretic analysis of the condition of free mobility that Poincaré derives from Lie reveals that it too is based on nothing more nor less than a freely chosen mathematical idealization of our rough and approximate sensory experience. We don't experience closure under the group operation in ordinary experience, right? Still less if it's a continuous group. And in the second place, even with such an idealization already in place, there is still no way for Poincaré that our actual experience of such displacements can then discriminate sufficiently between the three classical geometries of constant curvature. Rather, we stipulate or postulate Euclidean geometry by convention as the simplest and most convenient idealization available of our inexact sensory experience with which it is consistent. And more generally, geometry for Poincaré is far too entangled with lower-level considerations belonging to what he calls empirical physics, involving the physical rigidity of real material bodies as opposed to their mathematical rigidity, to enable a straightforward empirical determination such as the one apparently envisioned by Helmholtz. The final two levels of Poincaré's hierarchy of the sciences after geometry comprise mechanics, which for Poincaré means Newtonian classical mechanics, to which he himself made centrally important contributions in mathematical astronomy, stability and lack of stability of the solar system, and the more experimental parts of physics, such as theories of particular types of empirically given forces. At this point, Poincaré says, we arrive at the physical sciences properly so called. Here the scene changes. We encounter another kind of hypotheses, which are by no means definitions in disguise, and we perceive all of their fecundity. Moreover, the main example of these physical sciences properly so called come from the development of optics, electricity, and electrodynamics. This is by no means surprising, since Poincaré's most important contributions to physical science, as opposed to pure mathematics and mathematical astronomy, in this context comprise his own very significant contributions to the electrodynamics of moving bodies, which is, of course, the title of Einstein's 1905 paper. Einstein begins this paper with the example of the relatively moving magnet and conductor. That's right here. And Einstein says, the observable phenomena here, the current flowing through the conductor, depends only on the relative motion of the conductor and the magnet, not on which is really moving. Whereas, according to the customary view, the two cases in which either the one or the other of these bodies is in motion are strictly to be separated from one another, even though give the exact same empirical results. Thus, Einstein here appeals to a fundamental symmetry in the electromagnetic phenomena, which, however, is asymmetrically represented within the classical version of Maxwell's theory formulated within a Newtonian space-time framework with absolute simultaneity. This is a rather anachronistic way to describe what was going on, but I will show you some pictures which at least make it intuitive, but not quite yet. Einstein then introduces what he calls a principle of relativity in the immediately following second paragraph. You have the whole quote on your handout, you have it here, and I'm just going to point to the things that are underlined. He's talking about the phenomena that suggest that electrodynamics satisfies the same relativity principle that mechanics does, that is some kind of inertial principle. These experiments suggest, as has already been shown to the first order of small quantities, that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics are valid, that is Newtonian physics. We will elevate this conjecture, whose content will be called the principle of relativity in what follows, to the status of a postulate or a presupposition. Here, as Einstein suggests in a footnote added in 1913, he did not yet have knowledge of either the Michelson-Morley experiment nor the resulting approach to the Lorentz-Fitzgerald contraction hypothesis, appeals to it, to explain this experiment within a classical framework. For Einstein only mentions experimental results up to first order in V over C. He is already willing to conjecture, however, that the same results will be found for all orders, and he says he is willing to elevate this conjecture to the status of a fundamental principle, postulate, or assumption. Okay, we know that Einstein was intensively studied science and hypothesis in the years 1919 and 1902 to 4, that is leading up to 1905, as part of the curriculum of a discussion group dubbed the Olympia Academy in Bern, of a few friends of Einstein. And it appears very likely that Einstein had paid particular attention to Poincaré's treatment of electrodynamics. For Einstein, like Poincaré, is demanding that we here follow a rigorous extrapolation of the then known experimental results, according to which the principle of relativity is assumed to be valid for all orders of V over C at once, V being the velocity of the body, C light. Moreover, a general methodological moral of science and hypothesis, stated in Poincaré's general conclusions of the third parts, is that the fundamental principles of mechanics, this is now Poincaré, are definitions or conventions are drawn from experimental laws. These laws, so to speak, have been elevated, érigés, into principles to which our mind attributes an absolute value. It appears from Einstein's language, namely erheben, that he is in fact following this methodology quite properly. I take it that one is a translation of the other. Yes? That érigé and erheben are synonymous. Okay, or usually translatable. So this is suggestive that he was familiar with that passage, and there's further evidence for that. In particular, the experimental law in question comprises the contemporary results on the failure to determine the motion of the Earth with respect to the ether. These, like all such experimental results, that's now after Michelson-Morley, can only be valid up to a certain order of approximation. Nevertheless, by postulating or presupposing that they are strictly and universally valid, we can thereby elevate them to a wholly different status. In this case, the presupposed principle of relativity, together with a light postulate, then issue in what Einstein calls a new definition of simultaneity in the immediately following part, number 1 of part 1, which arises, as Einstein himself emphasizes, insofar as we stipulate, festsetzen, by definition, that the time light takes in traveling from A to B is the same as the time it takes in traveling back from B to A. A more perfect implementation of Poincaré's what we might call elevationist methodology against the background of Poincaré's own conception of the role in electrodynamics of what he too is now calling the principle of relativity, valid for all orders, could hardly be imagined. Well, not so. Yet Einstein is implementing this methodology. The way he does it is completely at odds with Poincaré's carefully crafted conception of the hierarchy of sciences. In particular, Einstein explicitly avoids any consideration of the theory of the electron and thus does not implement this elevationist methodology at the level of electrodynamics itself. It was the great Dutch physicist Hendrik Antoon Lorentz who originally developed, the theory of the electron, and he, Lorentz, posited an explanation of the famous Michelson-Morley experiment in terms of length contractions and time dilations operating at the micro level of electronic and molecular and atomic structure. Poincaré followed Lorentz's lead here, and his most important contribution to what we now call special relativity concerned precisely his articulation, the way he articulated the deformable structure of the electron, which would supposedly explain the contraction hypothesis eventually at a fundamental level. And so in this 1905-1906 paper is where that is done. So it's on that basis, and you get a theory which is in effect both mathematically and empirically equivalent to Einstein's, although one is about electronic structure and the other isn't. Where necessarily we obtain, Moreover, Poincaré needed to implement his theory at the more empirical level of electrodynamics precisely because he, Poincaré, takes the relativity of space and motion to enter in at the earlier level of his hierarchy of Newtonian mechanics, where necessarily we obtain the Galilean group of transformations between inertial frames rather than the Lorentz group. Einstein, by contrast, implemented his principle of relativity directly at the level of the underlying kinematics of space-time and motion. This was all in what he called the kinematical as opposed to the electrodynamic part. Or, as we would put it today, at the level of the four-dimensional geometry of space-time, which Einstein isn't yet exactly using then, but I'm going to use it anyway because it's very intuitive. In this geometry in particular, Minkowski geometry, it is the light cone that is invariant rather than the planes of absolute simultaneity. So here the light cone is light going off with the constant velocity c in the particular frame number 1, which is supposedly at rest. Well, in the Newtonian space-time with absolute simultaneity, the velocity can't possibly be the same in the two frames. That little picture is supposed to suggest that. But if you allow the plane of simultaneity to tilt up at the same time that the axis of the inertial frame is tilting to the right, then the projections can give you constancy of exactly that. Right. So in this geometry, it is the light cone that is invariant rather than the planes of absolute simultaneity, and the symmetries of the Maxwellian electromagnetic field are now taken to be the symmetries of space-time itself. No theory of the constitution of the matter that fills space-time at the molecular, atomic, or subatomic level is needed, or at least not yet. However, another serious problem quickly became evident. Newtonian gravitational force is an immediate action at a distance through empty space. So the kind of causality involved here requires absolute simultaneity because it's instantaneous. And thus the underlying structure of Newtonian space-time, that is its causal structure, requires that. How then can gravitational force fit comfortably into the space-time for Maxwell's electromagnetic force? A number of physicists were intensely aware of this problem around the turn of the century, including Poincaré, who responded by looking for an electromagnetic explanation of mass and thus of gravity. But none of these theories succeeded until Einstein, in his general theory of relativity, 1915-16, reconceived the gravitational field in terms of a curvature, a variable curvature depending on the distribution of mass energy in space-time. Here you see it in space, which is very intuitive, but really it should look like this. Here's a black hole space-time from Gauroche, where you see if the light cones are tilting, and that's what's driving the light cone, the light rays. And now Poincaré's hierarchy has become definitely a thing of the past. For the level of what he calls geometry, even as we have seen purely spatial geometry, has now become a part of experimental physics. I have argued elsewhere that Einstein's creation of the general theory of relativity was intimately connected with his understanding of the early divergence between Helmholtz and Poincaré concerning the foundations of geometry, empiricism versus conventionalism. And I have appealed in particular to Einstein's celebrated Festvortrag of 1921, Geometry and Experience, emphasizing the role of his thought experiment of the uniformly rotating disk or reference frame, without which, Einstein says, he would have found it impossible to establish the general theory of relativity, unquote. I now believe that my argument, although correct as far as it goes, does not have all the philosophical significance I claim for it. And time permitting, I will say more about this, not now, you'll be happy to know, but if time permits, at the end of the second lecture. So thank you for today.
We're doing well on time, actually. So, questions? I'll keep a list. If you put up your hand. Anyone?
I don't think so.
I was just curious, given the advances in computer vision and the movement towards more statistical and empirical approaches, do you think there's any evidence for or against kind of the underlying nature of space versus these are just artifacts of our mind?
You mean space might not be a continuous three-dimensional map?
Well, I mean, does it?
Imagine that our perceptions may not really be.
Yeah, does it say anything about, is it just our perception that it's, because if you can simulate that with these mathematical objects, does that say anything about our perception versus underlying, the underlying
It
nature?
does say something about our perception, and I guess there are at least speculations that quantum gravity is going to require that we don't have space and time as primitive entities anymore, but we should have some discrete lattice-like structure instead. That could happen. Now, the way both Kant, well, all these people are thinking about it, because of course they're not living in our world at all, they're thinking that a paradigm of a priori knowledge, whatever it usually is geometry, analysis, all of these wonderful mathematical theories that have been developed and have been successfully applied in physics so far. These all involve various strong notions of continuity. Of course, we're conscious that when we apply them to nature, there's a strong element of idealization there. So there could be a gap between the idealized structures that we can mathematically describe and understand and nature. That's always a possibility. They didn't have any particular reason to think about that, but Poincaré in particular emphasizes repeatedly that there has to be an idealization from our actual experience to get to these highly continuous structures that we want to. So that's how they would think of it. They would say, look, if you look at physics so far, whether it's relativity, whether it's Newtonian, whether it's general relativity, whether it's special relativity, even if it's kind of ordinary quantum mechanics, right? Then it looks like we're still keeping continuous space and time. The geometries might be funny. The physics might be even funnier. But so far, so good. And so we'll go with that until we can't go with any. You always have to use some mathematical idealizations to do physics. So you're always in danger, but that's a good thing. You might find where the idealization breaks down, and that'll lead you something new.
So I'd like to understand better the Helmholtz's transition to the later view that there's nothing more to the principle of causality than just the regularity or uniformity in nature. I think when you were describing his original view about finding the ultimate causes, that connected immediately for me to a thought that wasn't at all conditioned by a Kantian way of thinking about science. But clearly for Helmholtz, the move to regularities alone was something to do with relinquishing Kant and something to do with understanding better understanding electromagnetism. Is that correct?
I wouldn't put it that way. You want to say
Well,
something?
then maybe I'm simply asking for a little bit more about Helmholtz's thinking there.
Good. He had in mind not just the law of causality attributing to Kant, that is the second analogy. He had very much in mind the metaphysical foundations of natural science. And so he took that to be an essential part of Kant. And in the first edition, he's very strong about it. It has to be these kinds of forces. And he gives the same kind of a priori force argument that Kant gives in the metaphysical foundation. Namely, ultimately, there are going to be two mass points. these mass points are going to act along a straight line. They can't rotate, although they could rotate around something. So what can they do? They can go toward or away from the center. So those are the two things now, that they have to be time independent. That's not so obvious, but that's what both Kant and Helmholtz thought, and they thought that if it's going to be conservative, it has to be. Of course, if you have those central forces, you do obviously have a conservative system, but not vice versa. So he thought that there was a bicondition. And then things that were pointed out to him as electromagnetism was developing convinced him it wasn't a biconditional, although he still thought that we could do that reduction. He wanted to leave that open. And he wasn't clear that the Weber-Ampere view was essentially in tension with Maxwell's view. Nor did anybody realize it until about 1882.
So in this move, it seems like two things are going on. On the one hand, there's a move from thinking the regularities have to be a certain way to having a much more wide open conception of how they might turn out. And that's what you've been talking about. Also, I was reading into it, possibly incorrectly, a move from a more, I want to say a more metaphysically robust form of causality, although of course, when talking about Kant, that would have to be, scare quotes would have to be introduced around metaphysically in some way.
It has to be a necessary connection for Kant.
Yeah, so that's
pretty robust.
Great.
It depends on what he means by necessary connection, but yeah.
So from that kind of conception where causality is bound up with the necessary connection to something that looks on the face of it, but I'm really just going from the quote here, to just mere regularity.
Yeah, it's not mere regularity for Helmholtz. It has to be a completely universal law, because to comprehend, but that's only a regulative principle. That is, there's no guarantee that we will be able to comprehend nature by truly universal laws. But that's the condition of the conceptualizability of nature, because what is a concept? A concept is a universal law that applies to everything that's in its extension. So he connects concepts understood that way with universality, and therefore, as a regulative principle, if we're going to understand nature completely, to conceptualize it completely, there must be exceptionless laws and the right concepts there. We may or may not find them, but it's a condition of the possibility of comprehending nature.
Still, universality still falls short of necessity.
He doesn't use that word necessity, but he does take it to be strict universality.
Is he giving up on
exceptions.
Is he giving up on a kind of necessity in favor simply of universality, though?
Well, this is a good question. You're making me think, because my mind is racing, trying to see if he ever talks about it. He says there's a necessary, space is the necessary form of our intuition. He uses necessity there. He says it is necessary for the comprehension of nature, but that's not of necessity. That we be able to have exceptionless laws. Whether there's, aside from exceptionlessness, another thing that we could call necessity in concept. Now, of course, Kant in a certain way equates strict universality and necessity. So it's a tricky issue. I don't see Helmholtz, at least I can't remember, or addressing that kind of issue which is important to us now, and was important to Kant. Although, as I say, he kind of equated necessity with strict universality.
Thanks.
Come to you next time.
Hi, Michael.
Anya, I knew I could count on you.
Yeah, right. I just wanted to ask a little bit about what happened to Kant when we moved to Helmholtz and Poincaré, and in particular, what's different between these guys, how they extend the Kantian project. So one question is about what exactly the constitutive principles turn out to be in those two guys. And so if I understood you correctly, for the Helmholtz case, there is one genuinely necessary constitutive principle that's left. That's this postulate of free mobility or constant curvature, whatever you want to call it. But then what curvature space actually has is determined empirically. In Poincaré, we can choose what curvature we want to work with. So that's a conventional choice. But so those would be then the constitutive principles on the Poincaré picture, right? Except that they are now not hardwired in our mind. There's now some choice, but those perform the function of the constitutive principles. And then the first question there will be, does Poincaré also have one absolutely necessary constitutive principle? So, you know, that whatever, we need to work with Riemannian space or something like that. Is that maybe the one for him that's absolutely necessary? So that's the first part of the question. Can I ask the second part directly? So the second part would then be what happened to the idealism? So given that both of them still have the story about constitutive principles in some way or other in there, the question will be, so what exactly does that mean to talk about constitutive principles and what exactly is constituted? And so Helmholtz, especially this, when you talked about, you know, him picking up the distinction between appearances and things in themselves, he really seems to go idealism here. So, you know,
I take it to be a transcendental idealism pretty similar to
straightforwardly.
Not the same, of course.
Right, but then interestingly in the Poincaré quote that you gave us there, this is number 10, he says, let us understand one another. These decrees are imposed upon our science. They're not imposed upon nature. And so it looks like that a really crucial difference between Helmholtz and Poincaré would then be that somehow Poincaré does want to paddle away from the idealism. So he is somehow buying into constitutive principles of some kind, but we don't want to constitute nature anymore. We want to just talk about our science. So then first, is that sort of how you are also thinking about it? But then how do we make actually sense of the Poincaré position? So if the conventions are to be understood as the heirs of the Kantian constitutive principles, what are we constituting exactly? Or what does this constitution talk then amount to in that case?
Okay, so what should I do first?
Maybe the first question, just a constitutive principle for both Helmholtz and Poincaré, what they are, and if you agree with the sketch I gave you, what they might be.
For Helmholtz, I think you're right that the closest he has to a constitutive principle is free mobility, in that that constitutes the possibility of the metrical geometry. He thinks. Of course, we don't actually think that's true, but that's what he thinks. So, of course, a Riemannian manifold that allows variable curvatures outside is not a candidate for a model of space for either of these. Right? So, I mean, if you mean Riemannian, if you mean something like spherical, but people usually now, Riemannian means could be a variable curvature, which wouldn't satisfy free mobility.
Right, so this is why I suggested that as a possible necessary constitutive principle on the Poincaré picture, because
he's quite clear about Riemann and his spherical curvature. He says, this isn't really geometry, it's analysis. Because it's a theory of these number manifolds. It's not a theory of space. Space is about a certain kind of experience we have. So that's roughly his attitude. So in a certain sense, it's off the table as a geometry for Poincaré.
Okay, so for Poincaré, then the constitutive principles are really only the conventions. There is no absolutely necessary underlying principle.
I would say for Poincaré that arithmetic is a constitutive principle. That's an absolutely synthetic a priori science for him, and it governs our experience and is connected to time and our experience of time, which relates to the possibility of succession. In something like the way Kant treats the pure intuition of time in relation to arithmetic, not exactly the same, but there's a kinship there, let me say. So our experience involves a kind of continuous unfolding time, and that permits iteration of arbitrary operations and therefore arithmetic. But that's constitutive in close to a truly Kantian sense. Same thing, I think, probably holds, maybe not as strongly for the next level of analysis, because there you don't really get any non-trivial choices of metric.
Okay.
But in the three-dimensional space, in the Helmholtz line theory, B theorem, then for the first time you get a non-trivial divergence of three and only three possibilities. And that's where the convention first becomes salient. It's not constitutive in constants. It's not synthetic a priori the way arithmetic was. it is a convention or definition in disguise. And furthermore, as you rightly pointed out, reading that passage, it's guided by experience. So his view is basically this, that in our everyday experience of the world, before we develop high-frequency physics, we're just there measuring the land. We're doing geometry. And it's important that we be able to calculate the areas of the fields and the silos, and we be able to magnetize stuff. And naturally, from that experience, Euclidean geometry, the Pythagorean theorem, all of that, suggests to us very simply and neatly. And it's the first thing you're going to think of. You're not going to think of some non-zero curvature formulas to begin with. And our experience, until you get very far in science, just happens to. So if there is a curvature, which there could be, it's pretty small compared to the space of our experience. And he even says, if we lived, in a Bolyai-Lobachevsky world, which we could, and which it had a much stronger curvature than our world, then we would have grown up with a Bolyai-Lobachevsky geometry.
Right, but there's still the part, I don't want to drag this on, but but there's still, since he insists that these are conventions, there's still this part of the Kantian constitutive feature, no longer the one that, it was hardwired and we couldn't have done it any other way or whatever, but the constitutive feature that it turns then out to be a feature of our scientific theory, that it's built in from the get-go and that enables the further.
But that's partly but that's partly in response to what our experience has been so far. This hierarchy has a kind of evolutionary time aspect to it for Poincaré. So, more primitively, we develop geometry before we're doing physics or anything fancy. There's no reason to think of any other geometry, or to use it, rather, in trying to reckon about our experience, that is, to calculate stuff about our experience. Let me finish for a moment. And that is conditioned by the experience we happen to grow up with. And then we become wiser and wiser. We start developing these heavy mathematical theories, and we get to where we're getting close to the velocity of light or whatever, and we begin to see that, well, no, there actually could be this different thing. And it actually is an option now, but we're not going to do it. Why? Well, because our ancestral experience already gave us that, and the rational way to do science is a kind of a Quinian conservatism, right? At a certain point, you have mathematical stuff that suffices for what you've got so far. It's working well. Once that's in place, it can help make more determinate the empirical science, because now you know how to measure stuff. Always use Euclidean geometry for measuring space, and then look for what you learn about forces and stuff like that from that. That's his picture. So it's a very complicated idea of it, as that almost begins to make it look, sometimes it looks like an arbitrary definition, but sometimes it looks like, well, it's almost empirical. All you're saying is, well, so our experience is kind of rough, we idealize it, then maybe we could change our idealization. But here he says that's not a rational way to do science, because the hierarchical structure, that's a Kantian element. You've got to have certain presuppositions. You can't, as it were, change everything all at once. So you have to keep constant certain very good old friends like Euclidean geometry. Then you're going to find out some new funny things about forces. You're going to make changes at that level.
Right,
So
but
enough.
yet we impose it on science. But I don't want to drag this on. I see the point you're making, but how about the second part? So you read them as ideals?
Helmholtz?
Helmholtz, yes, I guess you said already, but so Poincaré,
Well, Helmholtz, I think, has something quite close, if you buy my reading, which is not what all Helmholtz scholars do by any means. There's still room to say, well, no, there's actually an isomorphism. The real is actually whatever this is isomorphic to, but that's not how I read it. Because space is constituted by those perceptual space. So that view is close to a Kantian transcendental idealism, but the externality and the objectivity simply means it is spatial. And externality is giving, so it's an empirical realism about space. It's only a transcendental idealism about it, just like for Kant. But in the case of Poincaré, you don't see him doing that kind of stuff. He doesn't talk about Kant very much, at least in this context. Maybe he does in places I have. Okay, we have Tim with furrowed brow.
Okay, no, it's much more. Actually, you answered part of it, but I'm just wondering about the history because I don't know. I mean, you can see with Helmholtz, he has this principle of free mobility that restricts the possibilities. I'm just surprised. Were there discussions about variable curvature? You've got the possibility once you have Riemann's work, and you've gone beyond an axiomatic presentation.
Mm-hmm.
Were there other people discussing the possibility of variable curvature? Because it seems.
Well, Riemann himself speculates that maybe if we look into the microstructure of space closer and closer, first he says, well, maybe it would be discrete, or since it's not discrete, since we can't count the little atoms, it could turn out to be variable curvature. Why not?
Yeah.
So he envisioned it. People like Clifford talked about it. So it certainly was in the late 19th century a view that people talked about. They didn't really have an actual empirical application, though, that actually it was more than a speculation, except to some generalized what is it called when you do mechanics on the manifold?
Yeah. I mean, just wasn't it Gauss who sort of said, "Look, let's immediately go up on mountains and start, set up actual experimentally."
He wasn't doing axiomatic.
Yeah.
So in a sense, Gauss is imagining that.
Yeah.
So that was.
So was there sense in the zeitgeist that there was one way to go about this, and was there a fight between the empiricists and the people who were trying to impose some more structure on it, as it were, a priori?
That's a good question. My sense is that the philosophical controversy about empiricism versus conventionalism or some other form of some kind of a priorism took off with the Helmholtz-Poincaré exchange, if you like, kind of the debate across time. And that, I think, has shaped our discussion of conventionalism until now, rightly so. But of course, there was the possibility of using, because it turned out to be the actuality, but there was the possibility.
Does that magnitude apply to mass or just dimension? Like inertial mass and gravitational mass? We have magnitude up there.
Yeah, magnitude.
People measuring stuff.
Yeah, for any, you could take it to be a real number system, except he takes it to be arising from our sensory impression by just noticeable differences due to factor, by which we notice that things can seem to be equal to each other, but then on the next step, transitivity fails, so we have to posit some difference that we haven't perceived yet, and we imagine that we can blow it up and focus in on it, and so that leads to denseness. And then we have theorems that show that there are rational numbers, so that leads us to posit that as well. So he's got a story that begins with sense perception, because he doesn't want to think of mathematics as purely abstract. It's always related to experience somehow.
Anyone else? Okay, Chris.
So first I have a question about something you said in the questioning that maybe I misheard you or I'm just confused. I don't really understand. So
maybe I was wrong.
It was about it was about the Poincaré and the conventionalist stuff. You said something along the lines of if such and such were the case, we might have arrived at Bolyai-Lobachevsky geometry. What was the such and such at the beginning of that? Because I couldn't really make sense. I can't really make sense of it retrospectively. I thought for Poincaré it was like how space was entirely conventional. So it wasn't like things could be. Oh, okay.
So he's imagining a Bolyai-Lobachevsky world.
Uh-huh.
Do you remember this stuff about temperature world in Poincaré?
No.
The rods are contracting
Yeah.
as they move toward the. Otherwise, it would be a finite space, which contradicts the fact
Right.
that it should be a infinite plane. So, and the metric therefore has to incorporate that feature. So there's a kind of a funny projective metric that is brought in, and there's a temperature field. And he has his own version of the Klein model, where it's, instead of straight lines, it's these beautiful tessellations, these circles that are orthogonal to the circumference. And with that model is what he had in mind. So suppose we grew up in that world in such a way that that curvature was somehow detectable in ordinary life. So we're actually measuring stuff. The best measuring rods we have, we're measuring a field, and what? Pythagorean theorem is grossly not holding here. So they're not going to keep using Euclidean geometry.
Right, but then I'm struggling to see where the conventionalism is, because it's sort of...
because for us, Poincaré is saying, look, our experience of the history of geometry in our world is such that even fairly sophisticated, quite sophisticated applications of geometry to nature continue working and working for hundreds and hundreds of years with Euclidean geometry. And that tells us that the curvature in our world for Poincaré is, as it were, very close to being Euclidean in that sense. That is within that experiential realm. Now suppose we grew up in this Lobachevsky world where the curvature was quite strong. I mean, our world could still be a Lobachevsky, but the curvature would be very, very gentle, and it wouldn't be until you got to huge cosmological stuff that you would find it.
Okay, so I had another question, which I was going to ask before I got confused. I wanted to just ask a little bit more about the relation you were trying to describe between Poincaré and Einstein got a little bit lost on me. It went by a bit quickly. So the idea seems to be something like in the 1905 paper, Einstein kind of makes these stipulations.
Hagen.
Yeah, right. I got it was to do with Hagen, but I didn't exactly see. So it was more my
also for us,
for us, I presuppose, yes. The point I was kind of confused by on the face of it is I thought of Poincaré as quite a radical conventionalist, that I didn't really think of Einstein as being along that model. Like he sort of says these things there, but as you said, he didn't know about the Michelson-Morley thing.
It's not as radical as we think if we take the fact that there's an empirical element. So when you get to, this is Poincaré. Now we're talking about mechanics, not geometry, but the fundamental, so it's one level down. And he thinks that the laws of mechanics are a little more empirical than geometry. They're conventions and definitions in disguise, but they are drawn from experimental laws. These laws, so to speak, have been elevated every day into principles. Well, Einstein must have read that, I'm saying. The fact that he uses their Hagen, and actually in geometry and experience, when he's talking about Poincaré, he again uses the word Hagen to represent Poincaré's position, which to me says he's got to have gotten this idea.
Thanks.
Now that doesn't give you the radical conventionalism of, and my story about that is, what he has that Poincaré doesn't have is, he is not wedded to that hierarchy at all, Einstein. He'll use anything that he has to use. He's not interested in telling us what are the a priori and what are the non-a priori part. He's interested in having good, simple, well-grounded mathematical theories of nature. And he's very good at doing that, up to a point.
Thanks.
Anyone else? I think you've pacified this usually.
I don't know about pacified, but perhaps exhausted.
And exhausted as well. But thank you for that extraordinarily rich presentation, Michael. We look forward to the denouement. Thank you.